short two words about myself. I've been teaching at Sykli since 2016. My expertise is in the areas of waste management, recycling processes, circular economy, and really my favorite area is material flows and material flow accounting and assessment and analysis. So this is really, and I have a technical background. I have a Master of Science in Technology, and in addition to that, I'm a vocational teacher. I need to make that smaller. Okay, today's I still have the old date on that as well. We were supposed to have it a month ago, and but today our topics are material efficiency and a little bit on how your companies can do work more materially efficiently in practice as well. And then we're going to look at material flows and material flow analysis and a little bit about life cycle thinking. So those there are different definitions for material efficiency. This is by Motiva, that material efficiency means that competitive products and services are produced using less material inputs, while harmful impacts are minimized during the life cycle. And I think this definition is actually quite good because it takes into account both that we need to use less natural resources, we need to have less material inputs, and it also emphasizes that we need to use less harmful hazardous substances, since the impacts on the environment or health during the life cycle and I think both of these also include that we should maybe try to replace natural resources by recyclables, and this way I think material efficiency is a very important part in not only recycling but in circular economy. Not the only part of it, but a very relevant part of it. This I picked from the EU websites. Basically, of course, we will not be able to cease using natural resources completely, but if possible, we should be try to replace some of them using recyclables and materials that are already in use. But raw materials, whether it's natural resources or other resources, are used for production. We produce products and we consume them. And of course, in a perfect world, we would be able to prevent waste from being born and use all the materials as well. This is, of course, also enabled by, we need to be aware of things concerning eco-design, and we need to be aware of different materials and different possibilities, and the environmental impact of different choices we make, which is not always easy. And I think this is one reason why environmental sciences are very multidisciplinary. We need to be able to cooperate with many different areas. And yes, of course, the more efficiently we use the natural resources and reuse the natural resources, which means basically that we use the resources that are from waste, for example, by recycling. We can possibly live longer. We have natural resources for a longer time. We can save money in the best scenario, of course. Hopefully create jobs and this way boost the economy. And I think the most important thing is we can respect the limits of our planet and start living more in a more smart way than we have, and more sustainable way than we have done so far. Actually, it's included in the 7th Environment Action Program. Turning this way, we must also understand that resource efficiency and material efficiency should be taken into account in every step of the way in all kinds of businesses and all kinds of production. And design better and smarter and more environmentally friendly products. And we also need to think about how to consume more intelligently, smarter, because if we keep consuming the way we do, it's really not very. And this way, it makes it very much a part of circular economy. Yes. Well, here we see that the global material extraction, this ends at 2017, but the amount of materials extracted has been growing all the time. And I think we need to make a very big change and to actually realize that we are consuming far too much, and there might be another way by using more already extracted materials. And I believe that this is possible. I don't think we can restrict totally the use of natural resources, but there is a lot of potential. We already have a lot of materials in use. Of course, it would be good to enhance resource efficiency, and there are different tools for doing so and different indicators. And I think these are still being developed also, these indicators, to be able to actually to assess the efficiency of our actions. Of course, measures that can be used to improve resource efficiency are by managing material flows, on a company level, but why not on a country level or global level as well? We need to be aware of the life cycle environmental impacts, and we can also calculate many of these. And of course, life cycle assessment is also a powerful tool here. I think eco design is very important in and more and more we need to take into account from that in the design phase already, that by making material choices, or making not only whether we are using natural resources or recyclables, but also what the entire lifespan of the product will be, and whether it will be recyclable in the end of the life cycle, making it live a new life cycle afterwards. And also, I think we need to pay attention to possible hazardous materials through legislation as well. For example, for concerning waste of electrical and electronic equipment. But I think we still have a long way to go, and it's not always very easy to take all different aspects into consideration. Of course, enhancing recycling and reuse is always important, and I think that is something that is integrated into all parts of these measures. Bioeconomy and renewable energies are also very relevant, and I think especially today, I think we need to that we don't have energy resources for forever. Possibly we have for forever, but we may need to think of alternative options also there, and smarter options. And of course, I think not only developing innovation partnerships, but I think all kinds of cooperation and different kinds of partnerships, and sharing information and sharing know-how is very, very important for future, for eco-design, for managing life cycles, to manage material flows, and for the future. Circular material use rate is one way to calculate how material efficient we actually have been, and it measures the amount of reused materials, recyclables, basically, that we are using in our production. And it's actually been increasing on EU level. If we look at what's happening in Finland, we are not on a perfect level quite yet, according to this graph, but hopefully we will be getting there. In Netherlands, in this field, in Belgium. Well, if we look at material efficiency within a company, we really need to know what we are developing. So if we want to develop something, we almost always need to be able to measure it. Maybe it's not always true, but I think it's one way to. It's a very important way to develop these things. And of course, I see I have spelling mistakes. The one why we want to do it is, of course, we want to be more resource efficient. We want to use materials smarter, not only so that we use, but that we use the materials that we use them in a smarter way. We want to minimize the environmental impact of almost everything we do, especially for products and production. And I think we need to think about the environmental impact not only during the production and the product itself, but also during the use phase, and especially what happens once it is wasted, that whether it can be recycled, or what the recycling or reuse options are. We can also try to improve the processes, both of the products, to make them more efficient, so that we use less resources and produce less waste during the actual production process, and also during the production process maybe use less chemicals and water and energy and so on, to make it more environmentally friendly. But I think the main reason is to find new value and actually build the value from the possible resources that we have during the process and the production. And I think it's very important that we are able to measure and assess what the possible to be able to develop. Well, when we are assessing material flows, this is maybe a little bit simplified. We need to identify the material flows. We need to be able to measure them somehow, and at the same time, we need to also identify the costs. The costs are a very important part when we're talking about material flows and production. And of course, if we think about the production and producing products, waste is basically always a cost for the company. But if it could be a side stream, it could be an income. And I think this way of shifting, producing our product, but we're also at the same time thinking more about what are the other material streams that we are producing. Is it necessarily waste? It might be waste for us, but could it be something that somebody else might be able to use? And I think this way of thinking could be quite valuable. Of course, applications of material efficiency and calculating material flows, well, of course, for material efficiency or resource efficiency, but it can be also used for industrial ecology, or creating industrial symbioses, or building closed concerning material flows. This can be difficult. So of course, if the same materials can be reused in the material streams within the process or within the company, that could be one solution. And I think for many materials, this is actually the case, at least in the plastics industry and metals industry. But also different waters in the processes can be closed circuits, for example. Of course, we use it also for planning waste management or planning different recycling, and for this kind of applications. And I think this is one thing that already in the production phase of a product could be taken into account, on at least on some level. And overall for process optimization or production optimization. Well, different examples of material efficiency on an overall level, of course. How can we, or how should we reduce waste? And how can we optimize the use of raw materials? How can we make choices in what kind of raw materials we alternatives for what raw materials we are using? Could it be some recyclable? Could it be something close by, or does it need to be imported from the other side of the world, and so on? How can we expand the product lifespan? I think this is one thing that we need to think more and more about. According to legislation and different targets, we should try to use products as long as possible, and be able to repair them, and to expand. And this way, we don't need necessarily new products that fast. And I think in the past decades, it's been actually making an effort and repairing and thinking more about the lifespan of products. And also, I think material efficiency and resource efficiency is something that is very visible and in different logistical choices and transport and storage. And this is also a very effective way to think about resource efficiency. And actually, the economic significance of material efficiency is can be very big, because all the material that ends up as waste, we have also paid for the raw material. It's it can be of a large economic significance there. Of course, different aspects that are caused by wastage and loss. And of course, if we are looking at the production line, we do acknowledge the costs of waste management and the cost of raw materials if materials are wasted. But of course, if they go through the entire production line, we have a lot of other costs caused by this waste and loss. For example, labor costs. If we are producing products, they also have been produced, and we have labor costs. We have consumed a lot of energy for producing the waste as well. Manufacturing process costs, maybe chemicals, maybe water, and so on. Also storage, for example, and moving the material logistics has been done. We have been storing the raw materials. Maybe we have been storing even the waste, because even if we have sent defect products to our customers, then they will be sending it back. And this way, the costs are adding up all the time. And mostly, if we have a production unit, we are also paying rent, and maybe a lot of more costs that are here. So they do add up a lot. It's a lot more than just the raw materials and the waste management. Of course, if we're doing looking at the costs, one way of doing it is not only analyzing the material flows, but doing a total MFCA, material flow cost accounting. And this way, all the costs related to these any specific material flows in the process are also reviewed in the process and taken into account. And this way can calculate the costs for the material flows, and also allocate other costs to each material flow in the process. This way of calculating can be, of course, quite time consuming and it's and complicated. And of course, if we want to do something maybe a little bit easier that still tells us something that can be used for decision making, then maybe just material flow analysis could be the good tool to use. Here I have an example. I've been doing a lot of material flow analysis for different recycling processes and recyclables. And of course, if we're looking at, well, here I have some waste electrical and some different computer devices. I have a desktop PC, a laptop, an LCD display, and a CRT display. The CRT display, they are no longer being made, but somehow some of these are still ending up in recycling. I think many, at least in Finland, we are very effective on storing our waste electrical and electronic equipment at home before we bring them to recycling. So sometimes, or a lot of the time, even very old appliances are being brought to the recycling stations. Well, here we see that the material devices varies a lot, and of course the material composition, as well as the composition of different components define how we should recycle and treat the appliances. And of course, the material composition also defines what materials in our products are especially interesting concerning, for example, value, or maybe that they are some scarce materials, rare, maybe valuable metals. And of course, the way each device is built, and the material composition of each device also defines how they should be sorted in the beginning, because we only get a lot of waste electrical and electronic equipment and everything is mixed up. We have vacuum cleaners and computers and toasters and you name it. It will be very difficult to actually recycle these products and materials. But if we have a flow of just computers, for example, the composition or the treatment process will be much easier. It will be easier to pick the specific components with specific materials that we're interested in, and to recycle in a smart way. Well, for different materials and products, of course, if we have a product, I have the dotted lines are for the blue one is for aluminium cans, and the orange for PET bottles. If we have something that is recyclable with just one material, of course, it will be linear, the percentage of value in respect to the weight or the amount of material that is being recycled or processed. But as soon as we have a product with several different materials, we need to start making choices of what we want to recycle. Do we want to recycle a lot, or do we want to recycle value? And well, of course, optimally we want to recycle both. We want to recycle a lot of materials and, of course, the valuable parts. And for electrical and electronic equipment, there are certain components that contain most of the valuable metals, such as gold or platinum, silver. And to be able to concentrate these valuable metals, we need to get the components separated with these valuables, and to be able to recover them from the recycling process. And if this doesn't happen in the beginning of the process, then the valuables are lost. And this is actually something that recycling companies have become very good at. They do concentrate the materials by saving the certain components from certain products for a separate treatment process, and this way concentrating the valuable metals, for example. At the same time, when we have a lot of when we have products with several different materials, we also need to take into account that all materials are not, it is not possible to recover all kinds of different materials in the same recycling process chemically, because uh, the specific ways of recovering them mm, if of in some specific processes they are actually lost, and this way we need to also make choices that are we interested in recovering, for example, rare earths, or are we more interested in recovering the uh, platinum and gold. And but lucky for us, mostly the rare earths are in different components of the uh, appliances than the valuable metals. So this way it can be done. But if it were all crushed in the beginning without separating the separate components from each other, this would be, or this could be, impossible. I don't know what, 1:45. I don't see the watch. Well, going to material flow analysis, of course, the aims of assessing or analyzing the material flows is for us to be able to evaluate and recognize different options and possibilities as early as possible, and to impact design, for example. And not only design of products, but design of production processes, because if we want to optimize material efficiency, I think the combination of unit processes used for production, or if we are looking at a waste treatment process, of course, the waste treatment, we need to know our materials. We need to know the material flow. We have to recognize the different parts and its what we want the process to accomplish, and this way we can use material flow analysis to do this kind of planning and design. It can be used for decision making. It's a very simple process, or a simple way of calculating, but I still think it gives us very valid information that can be used for decision making. Okay. Well, of course, material flow analysis can be used for a lot of different things, and a process can be defined in many different ways. Can be a process can be defined. It can be an industrial process, or it can be a bigger picture and metabolism of a city or a human. It can be some kind of activity, for example, in a household or a treatment plant, or we can say a recycling plant or paper mill, and it can also be a part of environmental assessment. We can look at a part of the environment. actually in a lot of material flow assessment has been done also for materials included in a city, for example, buildings, and also for natural material flows and substance flows, such as nutrients into the environment, or nutrient flows in water bodies and things like that. And it can also be a service. For example, a collection process. I think most people maybe think of a process as a production process, so where we are producing some kind of product, and but any which way, whatever we are, however we are thinking about a process, whether it's an industrial process, production process, or waste treatment process, we can usually define it as, in a way, as a black box, and we don't have to think about what actually happens in the black box. We need to be able to define what goes into it and what comes out of it. This way, the inputs and the outputs are interesting when we're doing material flow analysis. And if we want to start analyzing better or more what actually happens within the process, then it can be divided into sub-processes and smaller parts. And this can also be done in material flow analysis. Of course, the main thing is that we should identify the different material flows in a process, and it can be, if it's a wastewater treatment plant, it might be the incoming wastewater in the process, and we might be interested in separating some substances such as phosphorus or and also, if it's whether it's a treatment process, well, it can measure loss or storage. Are we losing the material that we are wanting to recover? For example, in this wastewater treatment process, are we capturing all of the phosphorus that we are wanting to separate from the process, or how much is actually left in the water? And also on storage, can be also analyzed. But we also always need to define the actual specific system that we are assessing. I have an example of a waste management system, and within my waste management system is within the blue dotted line. So actually the produced waste production is not included into my system. That's actually the input, part of the input into the system. All of the produced waste is actually not included into the system, because some of it can be already used at source. It can be used for, it can be home composted if you have a home compost for biowaste, for example. Or in Finland we have a lot of saunas, especially at our summer cottages, so we can light the sauna with some waste paper. So this way our waste paper will not enter our waste management system. Or it might be just litter in the environment and might, because of this, not enter the waste management system. But most of the waste that is produced actually enters the waste management system. Some of it is separated at source. Most recyclables are paper, glass, metals, plastic, bio-waste, sometimes energy fraction. And well, what's left is what we call mixed waste. Sadly, it also contains a lot of the recyclables still, but is collected into the mixed waste. Most of the recyclables and also the mixed waste is actually collected at the residence. Depending on the size of the housing, we might have several of these fractions, or just mixed waste. And actually, the legislation is becoming being more becoming more strict. So I think more and more of even smaller residents will have more and more different recyclables to sort in future. But we also have these regional collection points, and some of the recyclables are collected by regional collection. Well, then I have simplified my picture a lot. Some of our material, of course, the bio-waste goes to biological treatment. I have not defined here whether it's composting or anaerobic digestion or some other treatment method. But we have biological treatment. Then we have mechanical treatment for source separated waste, maybe some of the mixed waste, depending on what area you live in. Doesn't mean that paper and glass and metals go to the same mechanical treatment, but we have different mechanical treatment processes. Those of you who are listening to me a couple of weeks ago, that we discussed a lot about these different treatment methods then. And of course, in all of these, we have, well, most of the mixed waste goes to thermal treatment. Some of it is produced into RDF, refuse-derived fuel, or some kind of fuel made out of waste. And then we can have then the mixed waste goes to, and maybe some other waste fractions end up in thermal treatment, into incineration. There are different options for that as well. We get heat and energy, and possibly after incineration, we also have some ashes, rejects, hazardous waste, not only from the incineration, but from maybe some of the other treatment processes as well. But most of our material goes to material utilization. And well, then once they are cleaned for material utilization, the materials end up in new products, but that is not included in this waste management system. So it's basically just the management and treatment processes for the waste. Another aspect of material flow analysis is substance flow analysis, SFA. And in SFA, we concentrate on looking at specific substances or just one substance in a specific system. And we, of course, have different aims depending on what we are looking at. It can be different problematic flows, for example, hazardous substances. Well, phosphorus is not hazardous, but in the wastewater treatment example, we are wanting to separate the phosphorus from the wastewater, and in this treatment process, it's it can be one substance that we are looking into. And of course, this way we can identify if we are actually being able to separate it efficiently or not, and also identify if there's a need of change in our process. Okay, back to our waste management system. Now, if we are looking at substances, I think very common is that our waste has, for example, cadmium and lead. Typical products where we have cadmium are batteries, of course, and lead. We have a lot of waste electrical and electronic equipment that still have lead, although lead is one of the materials that has been restricted in modern products to a minimum, but we still have a lot of products in use or being stored at households that have lead. And maybe we have other products that have these materials. And even though we have source separation, our source separation is not perfect. There are different. We can sort things falsely wrong at source, and then we might have the batteries in the bio waste, or I don't know, with the metals or something else. And then suddenly we do have some batteries and some waste electrical and electronic equipment also ending up in the mixed waste. And by doing a substance flow analysis, we can actually recognize and calculate where our hazardous materials end up. Do they end up in the materials that we are going to utilize, or maybe they end up in the landfill? I don't know. Maybe they end up in the through the incineration plants in the flue gases. Possible. Maybe not the heavy metals, but other hazardous substances. And this way we can recognize or calculate or at least analyze how these different flows are when we know the material composition in the beginning of our system. Well, this is an example of a material flow analysis, and it has been calculated with a STAN material flow analysis program. And I will later today show a little how this works. But here the process is actually the use process. The first blue arrow in the left is the put on market that says how many tons of computers, desktop computers, were put on market in 2013 in Finland. This does not say how many pieces of laptop computers were put on market. but everything, all the numbers are in tons. And so it's a mass flow system. It calculates mass flows and not pieces of equipment. And of course, we have the households that use the desktop computers. Then we have the first use is those who have store-bought computers. Second use, the second process or box shows the second use. That means that if I haven't bought my computer from the store, I've bought it secondhand, or maybe received it from my brother who doesn't need it anymore, but I think that it still works, so I could use it. And then we have this very sad box called storage, which actually contains probably a lot more than this calculation shows. That is once we have ended our use phase and the possible second use as well, we will still be storing it in, I don't know, in our homes possibly for years before we bring it to proper collection. Proper collection here means the not necessarily the recycling facility, but the collection points where they collect e-waste. For example, different waste stations here in Finland collect e-waste as well, and as well as stores where this kind of products are being sold also collect e-waste. And well, we have some other material flows here as well. We have the not proper collection. That means what is put into the municipal solid waste. Luckily, that is not a very large flow for desktop computers. It doesn't really surprise me because desktop computers are very heavy. They are like huge. They weigh 10 kilos approximately. So it's maybe not the product that you would put into the municipal waste in the household, but it's luckily something that most people actually then take to the recycling station or to the proper collection when they do separate from it. And then we have from each part, we also have the illegal streams, and illegal streams are very difficult to measure because, well, they are illegal. We only know the amounts that are actually being caught, and or the cases that actually are being caught. But I would say, well, in this graph, I know that the Puta market amounts are actual numbers. They are from statistics, and so are the in-use amounts for the households. Also, the second use phase for the households is a number that we have from statistics. The storage amount, basically, part of it is from statistics, but part of it is also collected through different interview material and interview research. And of course, if you ask someone, well, do you have a desktop computer in your household that you no longer use, but are storing, that you could take to collection? Most people, well, maybe they will remember their desktop computer, but a lot of e-waste devices, we don't even remember how many we have. I think most people may not have a desktop computer, but I think most people do have one or more cell phones at home. And I see there's a question in the chat. No, not illegal purchase, illegal waste streams, ones that is actually quite typical for e-waste. Illegal waste streams are ones that are not brought to the collection points where there should be. There are people who collect e-waste or basically steal e-waste, transport it to, for example, Africa or somewhere. These are illegal streams. I think also for example, everyone has seen pictures from Africa where e-waste is being treated in not very smart ways, and the illegal streams are those that we from our e-waste streams have been in through some way have ended up, for example, in Africa. There are also legal streams because, of course, if the appliances are still functioning, they can be they can be exported to other countries for reuse. But actually, these also end up being a problem in the countries where they are transported. Yes, I do think it's quite a small scale in Finland, but it does exist, and every now and then it ends up as a topic in the newspapers because, well, you only see those that get caught. And actually this is in some countries, for example, in the Netherlands and Belgium, where they have huge export by sea. They have really large ports. Have a really big problem in trying to catch illegal streams. Not only e-waste, but I think other materials as well. And actually, well, not only concerning e-waste, but I think these illegal waste material markets are actually globally really huge. And maybe e-waste is one that is topping it, but the globally illegal waste flows are quite huge. Not as huge as drugs and prostitution, but maybe after that. And one more question. Oh, great! I love it when. No, these are only the desktop computers and not the different parts, not the keyboard or the mouse or the screen, just the actual desktop computer, not connected to anything. So in this mass flow study, and actually this this was master's work done by a student at the Aalto University. I used to work at the Aalto University, and he actually assessed and analyzed the mass flows for several different e-waste products, and desktop computers was one of them, and he also analyzed the material flows for laptops and for MP3 players and for cell phones, and now I've forgotten something. Well, never mind. Anyway, for several different e-waste products or electronic products, and they showed quite interesting things. And he did a series of 5 years. That this example that I have here is for 5 consecutive years, and the example I have here is from 2013. But most of them were similar. For example, for cell phones, that the storage part was actually quite huge, which I think is quite interesting because we are not very good on returning our cell phones to recycling or to the waste management processes. We keep on to them and actually somewhat 10 years ago or so, I think a study was made on how big a percentage of cell phones actually were returned to recycling, and the result was in Finland was 7%, and in other countries, many other countries, it was a lot smaller. So I think most Finnish people have more than one cell phone not being used in their households. Even I have at least one, and I know where I should return it, so I have no excuse. So, but yes, I think this when we're talking about mass flows and material flows, they are always calculated as mass flows, and of course, if it's a small mass flow, it might be kilograms or grams or less. But in this study, the mass flows were so large that all the numbers are in tons. Oh, it's already 1:15. And of course, we see how also in the, for example, in the household's first use, we see how much already are being used in the households in the little the numbers that are at the bottom of the households phase. It says 4,235.47 tons are in use in households already in the beginning of 2013, and the amount put on market is 819.15 tons. And actually, this makes a decrease of computers by 232 tons in comparison to the year before. And this, because there's a decrease, it shows that we are already in 2013, we are buying less desktop computers than we did in 2012. And I think this is a trend that has been ongoing, or actually since the beginning of, I think 2003 or something like that, we have been buying less and less desktop computers and more laptops. And I think this is also a trend that can be seen for different different products, the trend can be very, very different. That laptops amounts are increasing all the time, and the desktop computer amounts are decreasing all the time. And then, of course, if we're looking at the amounts in the households, it's very different, because if we look at the pieces of equipment, I think we look 10 or 20 years back, and there was maybe one desktop computer in a household that was used by all the people living in the household. And now, today, everybody has their own laptop. So we have more pieces of equipment. They have maybe become smaller most of the time, but they are personal and not in collective use in the households. So this is quite a big difference when we are talking about electrical and electronic equipment. Oh, one more question. I love it. You're chatty today. Within the latest years, no, I haven't checked that, but I think we're decreasing a lot, because I think people don't buy desktop computers, well, unless, well, my parents did, but they are almost 80 years old. So I think my dad feels more confident using a desktop computer than a laptop. I don't know. Well, that's what he said to me. But the decrease is large. And I think desktops may be used in industry for certain processes or procedures, but most people use also laptops for work. So there's been a very profound shift in use here. And some products hardly exist at all anymore. For example, these MP3 players, they were very popular for a very short time. And I don't know, does anybody use one anymore? I don't know, does anybody want to answer a question here? Maybe not. But I don't think that they are being used today, because nowadays our mobile phones have so many different ways of using that we can listen to music on our phones, so we don't need a separate MP3 player. And well, maybe next page. Okay, e-waste. Here we see. Oh, I have a spelling mistake again. But the generation of e-waste concerning desktop computers, and here we see that. Well, if I pick, for example, a green line from 2000, we see that these computers, a few already came to recycling the first year, but most computers are not broken the first year they are put on market. The same year they are put on market, they are wasted a lot later. And this way we see that the lifespan of a computer, even though we know that even though we know that it's maybe, I don't know how long home computers are used, maybe 5 or 10 years, they break at different points and are brought are wasted, so to say, are brought to the recycling. Maybe when they are broken, but maybe not when they are out of use. But maybe we store them first for maybe another 5 or 10 years before we bring it to recycling. And this is why today in recycling and also in future, we, even if different hazardous materials have been, or hazardous substances have been restricted from several products, the products that actually end up in waste management and recycling, they are from so many different years, and that we cannot be sure of the material composition of each of these, which makes it from recycling point of view, in a way more complicated. Of course, they are the certain components and certain kind of materials that are used. But also, if we compare an IT product from the 90s to one of today, the product from the 90s only had like 15 different materials. And today there's 60 different materials or more in an electrical or IT product, and which makes it much more complex. The concentrations are smaller, and it makes it more complex to recycle. Not impossible, but more complex. And well, what you're seeing in this graph is that the amounts of desktop computers ending up in brought to recycling is also decreasing. Not only are the amounts that we are buying, but also the amounts that end up into recycling are slowly decreasing, because we have for a long time already, for some decades already, been buying more laptops and less desktop computers. So here we have the same graph for laptops, and actually the trend is quite opposite. We buy more laptops, and slowly the amount of laptops brought to recycling is all the time increasing. And actually the reason is very logical. The laptop lifespan is still at its prime, so they will. I don't think that different smaller equipment have been replacing it enough yet, not like iPads or things like that are. I think most people will still have a laptop even if they have an iPad or something like that. So, but a lot of different electrical products are actually being replaced by new ones, and they have it keeps evolving. So this is quite interesting about using STAN. STAN is a material flow analysis program, and actually this computer example was made using STAN, and I think it's actually quite easy to use, and it can be downloaded for free, which is I think an extra perk. Always things that are for free are, well, always not good, but it's also a positive thing. This program has been developed by the Technical University in Vienna, and they have been doing it for 15 years. The first version came 15 years ago. And well, if you are interested, there's also this practical handbook of material flow analysis, also written by the professors in the Technical University Vienna, Paul Brunner and Helmut Rechberger. And it can actually be found at least at the Aalto University Library, but well, if you're interested. Well, I think the best characteristics of this material flow analysis program is, well, there are a lot actually, but you don't need to know all the data because actually the program calculates the missing flows. You need to know enough to be able to do some calculation, but always you don't, if you know, even if you know the process, you may not have all the knowledge of all the flows. And this is where the program comes in handy. What I also think is great that we don't have to have all the data in the same units. In the computer example, the mass flows were calculated in tons, but if depending on what you're working on, you might have some mass flows you might know in tons, but some you might know in kilograms or grams or something else. And there's a big variety of SI units, yes, but still different units that can be used. And also you can use volume data if you have something in cubic meters or liters or so, but of course then we are calculating mass flows, so we do need to also enter the density of the material. Of course, if it's water or wastewater, it's very close to 1, but then we do need to know the density of the mass flow, or of the volume flow, sorry. So we don't need to know the quantity data or the mass flows for everything. If we have a process, we can define how many percentages of the mass flow is being separated, but we need to know it from a process. So if we are planning a new process or a new unit process to add to our process, we can make calculations by knowing that, well, this screen separates 70% of the material, and we can, by size, and we can actually analyze, or we can enter the percentage as a flow from the process. This way also, if we are modeling some changes into our process, we can actually calculate how and see what effect it has on the process in reality. And I think this can be very, very useful if we have a process that has, say, 10 or 20 different sub-processes or unit processes, and we, for example, a recycling treatment process. And then we decide that, well, actually, I think in this specific part, quite in the beginning, we would probably have an advantage of having another screen. And by modeling and it with this program, we can actually see what or calculate and assess in advance what this change in the process would mean for the material streams in the end of the process. And I think this is very, very useful. And also we can analyze different material concentrations or substances in the stream. And if we are assessing some substance in the material stream, we might not know that if we have, say, the wastewater stream is so and so many tons a year, but still we might have some kind of we might have the concentration of the phosphorus. We might know that it's so and so many grams per liter or something like that in the incoming stream. So we can analyze it so that it recognizes the substance material flow, substance flow in perspective to the material flow. And then we can also define different lengths of periods. It doesn't always have to be a year. It can be an hour or a day or a week or a minute if we are having a very short run process. So this also can be defined. And of course, if we have different input data units for our input data, then we of course also have to define well, what is the unit that we want the data to be shown in? Do we want it all to be tons per year, or do we want it to be kilograms per minute? We have very few different terms, actually 6 or actually 7 terms that are used in material flow analysis. And well, I think the most important ones are, of course, substance and good. I am very bad at using the word good. I always use material instead of the term as a terminology instead of good. But basically, that means the main material flow, the material flow. If we are assessing wastewater, it's the wastewater treatment plant, it's the wastewater. And then we are looking at, then we can look at the substance, and if we are looking at the wastewater treatment plant, then the substance can be the phosphorus that we are interested in the wastewater flow. Then we have processes. Here we have it's basically a box. It's not a black box here, but a white box. But it's shown by a box. We have flows or fluxes. We have 3 different kinds depending on the process, or how they are placed in the process, or actually in the system. We have input flows, export flows, and just flows that are designed to be between processes. This is because we always need an endpoint to each flow. A flow needs to go from somewhere to somewhere. And when we have a system and we just have a material flow coming into the system, we need an import flow to show that it comes from somewhere, so that it can mathematically calculate it. The same thing that if we have a flow going out of our system, we need an export flow to assess and analyze and calculate, to be able to calculate that that the program will recognize that actually this flow is going somewhere, even if it's going out of our system. And then we don't have any letters on the flows that are connected to from one process to another process. Then we have stocks, and it's this P1 that looks like it looks like my garage door. So it's basically if you have a stock producing in your process, then of course the input is not equal to the output if there is some kind of stock or storage in your process. And so this needs to be taken into account, and this needs to be the program needs to be able to calculate also a stock existing in your process. And then we can define our system by this dotted line. Actually, when I have been doing material flow analysis using STAN, I never use this system because I actually don't include into my I only include things that I include into my system into what I draw. So actually the system separation I think is not very necessary, but of course it can be used if you please. So that's simple. We can still say that, of course, substances can be any kind of chemical element or compound or unit, but it's characterized by that it's always an identical constitution and homogeneous. This is like, well, it can be the phosphorus in the wastewater. This way, of course, any kind of anything cannot, or everything is not necessarily a substance, like here PVC, because it is not defined. It can have other additives as well, and for example, drinking water, since it also has other elements in it than just H2O. Well, goods, that's our actual material flow. It can be the drinking water, it can be the wastewater, it can be the flow of computers through the households to the recycling plant. It can sometimes it doesn't have to have economic value, but of course, if we're looking at treatment processes or production processes, it's more interesting to look at our raw materials or the input materials that have economic value. Well, basically, material can be used for both substances and goods, but I try to not use material for substances because I use it more commonly for goods. But it's your choice how you use them. So basically, we have a process, and then we may have sub-processes. And the idea is that the input and output, they should always be in balance. If the input is bigger than the output, then we have something storing into our process. And then if the output is larger than the input, then it is picking up something from that is being stored in the process from before. And well, of course, once we have defined our input and output flows from the process, we can start thinking, well, what kind of sub-processes do we have in this process or system? And then, of course, the flows within the system can be different. But even here, even though we have 3 sub-processes that are interconnected, the input flows and output flows are the same as in the original system. Well, I talked about that we can have design a stock into our process. So if materials are being stored in the process, say like for example for landfill, I think one of the best examples is the incineration plant, because the incineration plant has a storage for the waste that is being brought. That when new waste is being dumped into the storage, the stock is increasing, and once the waste is lifted onto the crate for incineration, then the stock is decreasing. And I think this kind of stocks are very common in many processes, that we can have both increasing and decreasing of the stock. Well, typical for MFA for the program to be able to calculate anything, our first assumption is that the input is equal to the output. But of course, if we have some changes in the stock, then the stock will define the difference in the input and output. Here, for example, we have input flow of 18 units, tons per year. It doesn't say what it is, different materials. And we have outgoing of 48, which makes that it needs to it kind of eats the stock change is negative, and the output, because the output is larger than the input. This could be, for example, the incineration plant where the on this specific year more has been incinerated. I don't know. Okay, we'll go on with life cycle thinking. Then next topic. I can't see what time it is. It's already 2 o'clock. Well, of course, the one aim is to minimize the amount of waste and to produce products in a way that is more environmentally friendly. And actually, once we are often thinking that thinking of what environmental risks there are, or health impacts, or what the production looks like. And I think life cycle thinking is, we need to think of the production phase from the very beginning, from extraction of raw materials through the production phase, through the use phase, and all the way to the waste management phase, in a way that that to minimize the environmental impacts of the the um, the product, its use, and its waste phase. And of course, this is a big task. We need to know a lot of things. We need to know a lot of facts about our product. We need to know a lot of facts about producing our product, about the production chain. We need to know things about the use phase, and we need to know and analyze different waste treatment options or recycling possibilities. And then we need to also understand what kind of impacts these things have on the environment. So it's not a very small thing. And of course, that the process is similar whether we're looking at some electrical and electronic product, or we are looking at food or whatever. But I think the life cycle thinking, we should expand to thinking about all kinds of more abstract processes as well, like we could have it for a meeting, or for, yeah, we could think about this meeting, for example. And it's a motivation to I think it's very common today that we want to take the life cycle into consideration in decision making, and we do want to be as sustainable as possible. And I think the motivation should be life cycle sustainability, and we should maybe try to consider that it is an opportunity to do the things in a smart way, and not consider it a threat in itself. But we do need to acknowledge the environmental impacts of our products and of our processes and of our activities. And we can, for example, analyze the production or the activity using some kind of simplified LCA, life cycle assessment. But we can, but it doesn't have to be a full life cycle assessment, because it's that is often quite complicated. It goes very deep into different aspects and is very time consuming. So I think maybe a lighter way, of simplified way of looking at it, would be good. And this is a way of finding ways of improving our environmental activities. Well, what do we really need for future sustainable development? Of course, one possibility of life cycle sustainability assessment, and of course, compared to that, environmental assessment, life cycle assessment is very much more simple. Into this life cycle sustainability assessment, we should also be aware of costs, make a life cycle assessment type life cycle costing, and also be able to assess the societal impacts of the life cycle. And that's a lot of parts. But we have different methods. We already talked about material flow analysis and substance flow analysis, and how we can assess the different materials or material flows, how we can be more material efficient and avoid hazardous or harmful substances. It can also be a way of finding how we can collect or how we can save the valuable substances, and maybe some materials, some substances can be both harmful and valuable. I would say, like phosphorus, for example, we do need to get it out of the wastewater stream, but that material flow. But in itself, phosphorus is a valuable nutrient, and if we can get it out of the wastewater stream, we might be able to use it for fertilizing purposes, for example. Okay, life cycle assessment might not be the best tool in all situations, so maybe material flow analysis is a good tool. And of course, we do calculate different kinds of footprints. I would say that, for example, carbon footprint calculations are very similar to those of life cycle assessment, but we are concentrating on the carbon output, and well, then we have different thermodynamic methods, how to use energy more effectively or reduce the needed amount for heating or cooling or lighting, or maybe how to use renewable energy. So we have a lot of different tools. If we want to use the information for decision making, for example, life cycle assessment, we need to. There are some limitations, and of course, we need to be quite open about what we have included and what we haven't included. This way, it needs to be openly reported, because it's very difficult to draw any conclusions if all the information isn't available. Life cycle assessment is actually a very good tool for company to market quality and maybe the environmentally friendly products, or to illustrate why some investment in a product is maybe more profitable for the customer. But and also it mostly communicates a high level of environmental management, and this way adding to a positive image. So it's it can be used in marketing quite well for companies, and it is used for marketing, telling, well, hi, we're doing things in a really environmentally friendly way. Our products are great. But of course, if we're looking at a company, it can be used for product development. We can recognize that some of the raw materials might not be so environmentally friendly, or something is being transported very far and we might be able to replace it with more environmentally friendly raw material or component that we get from a little bit closer. We can also make some comparisons between alternative products or processes, but this is of course only if the life cycle and assessment has been done in the same way. If they are done for different companies and the scopes are different, they are not necessarily comparative at all. So this is of course one problem. But within a company, products and processes can be compared, can also be used for strategic planning, and or for companies when building environmental policies or thinking, planning their products. And of course, it is also used a lot for marketing and for marketing and to get the customers to acknowledge the best environmental perks of the product, for example. And they're all very often included in different environmental programs and environmental labeling. So this is how they're being used. Yes, I have a comment. Non-profit organization, I don't know. Yes, many companies do there are different environmental labels. Some are more commonly known in Finland. We have the SWAN and I don't know what these are in English, but there are different kinds of environmental labeling, and they have very different meanings. And also, life cycle assessment can be used for promoting environmental labeling, environmental labels. I can't answer that more exactly, but yes, there are companies that calculate life cycle assessments, and there are many consulting companies that do it for other companies, and I think that that is maybe the most common way of doing it. But I think today, actually, maybe I'm wrong, but I have noticed that more and more companies are actually more interested of the carbon footprint and their carbon dioxide emissions than just life cycle assessment. But actually, the methods are very much the same. Only the environmental impact is considered only as an environmental impact. Only carbon dioxide equivalent emissions are taken into consideration. And of course, this is because as it is today, I think one of our biggest environmental threats is global warming, and of course we do have other big environmental problems or threats concerning biodiversity and so on. But I think global warming is something that very many companies are very, very much aware of. Maybe the next thing that we will become more aware of is something else. And I think this is something that goes in. There are different things that we are most concerned about at different times. For example, I was doing my studies mainly in the 90s. So I think there wasn't very much talk about global warming yet at that point. I think the biggest environmental threats were things like in Finland we were concerned about sour rains due to our forest industry, and we were afraid that trees would die. And then, of course, eutrophication was also, we were in Finland at least concerned about that our lakes would suffer. And I think that we have different concerns in different times. And but for a very long time now, I think our maybe most concerning environmental threat has been global warming. And I think this is why many companies prefer, instead of making just a life cycle assessment, concentrate on the carbon dioxide equivalent emissions. So, but they're basically very similar, or actually quite almost the same. Only the we don't consider the whole environmental pool. Well, mostly we look at life cycle assessment, we impact from cradle to grave, but it can also be made from cradle to cradle, or there are different versions. I think I have it in a later slide. But it's a tool to systematically assess the environmental impact, or it can be of a product or a process or an activity, or well, basically anything. There are different variations. I have cradle to grave, cradle to gate, cradle to cradle. With cradle to grave, we mean from the extraction of raw materials until from over the whole life cycle, the production and use phase until it is wasted. And cradle to cradle is assuming that the loop is existing, that we are actually planning the recycling or the use, the next life cycle already. And the carbon footprint is something that is coming, is now actually coming maybe stronger than life cycle assessment itself. Well, mostly if we're looking at a product, we are looking at the production chain. We first test the raw materials acquisition and the manufacture, and then the product use phase, and then possibly the final disposal, hopefully reuse or recycling. And in all phases, we probably use energy and maybe chemicals and additives, and waste is produced, and but also in some phases we can maybe choose to use some recycled materials or recycle, reuse some components or parts, and this way minimize the environmental impact. For all kinds, any kind of LCA, we need to define the goal and the scope of the research, the functional unit, and we have to set system boundaries. And this is, of course, why different products for different companies made by different people cannot be compared cannot be compared, because that we don't know. We need to read the whole study, or maybe we don't even understand it after reading the whole study, exactly how all the systems, the boundaries have been set, and so on. So the results may not be comparable. And of course, here also in life cycle assessment, I often say that material flow analysis is the base for making life cycle assessment, because we do need to map the material flows and also the energy flows, and everything that happens in the process, everything that we include in our system boundary. If we have transports included, then also the transports and so on. And then the last part is the impact assessment, and of course the interpretation. Well, if we want to get started with the life cycle assessment, there are numerous different softwares for doing life cycle assessment, and equally as many databases, or maybe more, I don't know. I think if you want to do a very simplified inventory, it might be enough if we work with data from databases or inventories. But to make a complete life cycle assessment, we should be collecting specific data, or product specific or process specific data, as much as possible. And this can sometimes be very time consuming and very complicated. And also, I would say that if you're using databases, the results can be very different depending on what kind of material you get from or information you get from the databases, or how old it is. Does it represent geographically the area, the material or the transport or whatever from the area that you are where your raw materials are from, for example? Does the energy grid represent that of your process use today? Also, the energy grid for different countries changes with time. So if we use database information from a few years ago, it will look different than the energy grid today, for example. And so this is one challenge when we are making life cycle assessment. How much do we rely on set information, and how much we actually collect product and process specific information, and how much or what do we have available. But also, depending on what kind of life cycle assessment we are doing, we can choose different softwares, and there are different softwares that are suitable for different areas of different industries or types of product. So it might not be best suited to always use the same program, but of course, if possible, it might be smart to use a program, software and databases designed for that specific field. Well, again, a graph of how life cycle from cradle to grave could look. We have resources and use of chemicals and components, semi-products that all go to the production phase. I have these circles where use energy in different phases. We have transports, are the green T's, going along, and waste is produced in different phases as well of the production and use. And of course, some of the waste in the different production phases and use phases may also be able to be recycled or reused or utilized some way. So it might not be disposed in a landfill, but there's a lot to take into consideration. And I think that one thing that is often maybe not true, but often maybe a little bit underestimated in many life cycle assessments is other transports. That the main that we are concentrated so much on the raw materials and the production that that the impact of the transports is considered to be quite much smaller than it maybe is. I don't know. Of course, we have very, this is an old picture, but it's only to show that we have very different types of products. And of course, what kind of impacts they have on different, in different phases, and yes, the line that is falling, this red line, is an example on effect on climate change for a food product. For basically the raw materials and the production space is the most climate intensive or intensive phase of the life cycle. And well, the use phase and the waste treatment phase is not so much, because mostly hopefully we eat the food product and it doesn't end up as waste. But for example, if we have an electrical product of car, for example, the balance is quite different. What I mean is that, of course, the raw materials here, maybe they have an effect on climate change that might even be larger than that of food. But if we, in Finland, we often use cars up to 20 years. So during the use phase of the car, the emissions and the effect on climate change exceeds that of the raw materials by far, at least when we are talking about a traditional car work with using fossil fuels. Then if we are looking at an electrical car, it might look quite different. Again, then we have the batteries that are have an environmental impact, maybe not so much on climate change, but other environmental impact, and maybe not so much in the use phase, depending on what kind of electricity we use. But so also here, that if we would choose to make a life cycle assessment only for the production phase or from cradle to gate, then we would miss the entire use phase, which can give a very different result for that specific product. And this is something that I think that we need to be able to analyze and understand how the boundaries have been set, and how the life cycle assessment has been made to be able to assess the actual environmental impact. Well, who do we really want to convince with the life cycle assessment? Well, of course, the shared values is, of course, important. But of course, maybe we want to convince the authorities that, hey, we have a really, really great product, or we have a great process, and we are doing environmentally great things. Or maybe it's the shareholders or customers that we want to convince that, hey, we have a great product. Or maybe it's the neighbors for our factory that we want to convince that, hey, our process is really, really great. Or maybe technology producers or insurance companies, and so on and so on. Well, what is the consumer perspective? What does the consumer want to know? And how green is the consumer? Or what is the green consumer behavior? Do they want to know what the environmental impact of the product is? They actually maybe want to compare. Do I want to buy this brand or that brand? But this is, of course, something that the life cycle assessment might not even say anything about, or it doesn't give the answer. Or which solution has the lowest impact? I think these are things that consumers are quite interested in, and I think, for example, concerning carbon dioxide or greenhouse gas, we are very aware of global warming, and we do want to know what kind of products we are buying. And I think more and more of the grocery stores and things like that are trying to give this information to their clients, if not now, at least in near future, so that we would have a better chance of making environmentally sound decisions, because it's not very easy to know what products have the smallest impact. And it's not always easy to know what activities have the smallest input either. Is it better to dishwash by hand or by dishwasher? Mostly probably dishwasher if it's fully loaded and using an environmentally friendly program. So probably we will use at least less water. Well, from the industry perspective, of course, they want to know more about their product, and they want to better be able to identify different hotspots or take into consideration these environmental aspects, and also how to use it in marketing. And this is something that I think that many companies do use it in marketing, and the consumers have a very hard time trying to actually interpret what everything means. And now, of course, things that can be included in the environmental management system. I think the ISO 14000 group of standards is maybe the most common ones, but we have other environmental management systems as well than just the 14001. We have, for example, Green Office or other environmental management systems, depending on what the companies choose to use. I think choosing different kinds of tools to assess the environmental impact or to use for decision making in industry or to use for communication, for marketing, it's not at all easy. It's a big challenge to make it as simple as possible, but not too simple for it not to mean anything. And we have to balance between what is the absolute truth and what we are trying to market. So I think a company should always think first, not just go and start making a life cycle assessment or material flow analysis or carbon footprint or I don't know what, but should actually think about, well, what is the what do I need it for? What do I plan to use it for? So that was actually what I had to share today. Oh, it's almost 3 o'clock as well.